Hi all. I welcome all of you to the presentation of our work titled Semantic Labels-Aware Transformer Model for Searching over a Large Collection of Lecture Slides. While plenty of lecture slide presentations on various topics are available online, searching for a relevant and compelling slide deck for a given query can be tedious and time-consuming for educators and students. The motivation for this work is the need for an efficient slide retrieval system that accurately retrieves slide images for a given query. Efficient slide retrieval has versatile applications across multiple domains. One such application is the automatic generation of classroom presentations given a topic. The retrieval system can easily access various presentation ideas on a topic and efficiently combine them to generate a new slide presentation. Generally, the slide images are retrieved using query words or sentences. However, there is no approach to retrieving slide images using sketches. The best queries for the slide image retrieval. To understand the best queries for the slide images, we show the slide images to the annotators and ask them to write a single sentence summary about the slide image. They have annotated 20K slides with summary. We analyzed the summary and got a very common pattern topic explains using logical regions. To recollect a slide image, humans use logical regions, keywords, and a rough sketch of the figure appearing on slide images. The figure shows the annotation pipeline. First, the annotator write down the summary of a given slide image. If a figure is appearing on the slide image, they will draw a rectangular region around the figure and draw the figure in a white paper. Comparison of our LecSD dataset with other slide datasets are shown in the first table. Here it is noted that most of other dataset retrieve slide images based on the transcript which obtained automatically. Our dataset is unique in terms of having manual summary and sketches of the figures. The main challenges of our proposed dataset LecSD. The main challenge is the presence of logical regions in the summary. It does not have a unique and specific label. The block diagram can be named as figure schematic diagram or simply diagram, etc. We selected lecture slides from data structure course to increase the dataset's complexity, especially due to their similarity, which creates challenging negatives for retrieval. The similarity among slide figures further amplifies the difficulty of the sketch-based retrieval task. Here is our problem statement. We aim to retrieve the most appropriate slide image from the dataset given a query. Let the dataset K consisting of a description of slide AJ and the slide image BJ. The description AJ is the text description T and the sketch description S. Hence, the system supports both natural language and hand-drawn sketch queries. The goal is to learn an embedding space that can quantify the similarity between the slide image and description. As a result, given a description, text or sketch, or both, AJ, one could retrieve its similar slide images from the dataset K. Here is our proposed baseline architecture for the design problem. In the dataset indexing, we collect the logical regions TL figure type TG and OCR text to information along with the slide image B and a focus area BF from each slide image. The focus area of a slide image is the most plausible logical region where the keyword is occurring. We use the vision and language transformer model to encode these text and image inputs. The PIENet encodes the local and global features for text and sketch queries. We optimize our model to minimize the multi-instance learning, MIL loss, maximum mean discrepancy, MMD, and diversity loss. In the training slide images of LecSD dataset, all the slide images do not contain figures. Hence, we first train the VILT and the text PIENet models. Finally, the sketch PIENet models learn during the fine-tuning of the whole network with slide images having both summary and sketch queries. In the inference stage, we calculate the similarity of query vector and the indexed image vector and rank the database. The ablation study. The table shows the ablation study results of the experiment to quantify the contribution of various features such as OCR text, TO, layout region, TL, graphics type, TG, and the focus area BF. In our experiments, we measure the retrieval performance in recall at 1, 5, 10, and the rank median. The first row of the table shows the result with the feature of OCR text and slide image, and obtained the recall at 1 is 22.35%. After adding the focus area feature, the result improved to 23.28%. Adding logical regions and graphics types improved our final result to 26.46%. We got a 4% improvement by adding the extracted features. We compare the proposed retrieval model with existing cross-model retrieval models on LecSD dataset, and the results are reported in the table shown. We trained all the models with our training data of slides from the data structure topic. We tested with the manually annotated slides from the topics, including data structure, computer networks, and optimization. The proposed model outperforms the existing cross-model retrieval approaches. The polyvilt and PVSE models perform reasonably well when retrieving the natural images given a caption. However, these models are unable to learn logical regions from slide images. Hence, the performance was reduced, indicating that layout segmentation and document figure classification modules are essential for slide image retrieval tasks. Compared to all other approaches, our proposed model outperformed in retrieving slide images for all the topics. However, here, we notice that the generalizability of this retrieved model could be better. The model drops its performance for the topics not included in the training set. Sketch-based slide image retrieval. This experiment is performed on the slide images with sketches and textual descriptions. In our dataset, we have the train, validation, and test have 5607, 1557, and 1487 slide images with figures, respectively. As shown in the table, we obtain recall at 1 as 37.05% in summary-based retrieval, and for the sketch retrieval is 23.63%. In the combination of sketch and summary queries, we got a result of 41.5%. Here, we notice that the sketch-based retrieval does not perform as summary-based retrieval. However, the combination helps to retrieve the slide image efficiently. Qualitative results. The figure shows the sample queries and the retrieval results. First, we gave the query of pseudocode for printing vertical numbers. The top 4 retrieved slide images are shown in the first row. The slide image with a green border is the ground truth result for the given query. The second query is implementing a stack described with a block diagram. The middle image row shows the retrieved slide images. Here, all the slides have block diagrams. However, the ground truth slide is retrieved as the 4th rank. Here, we provide the sketch query and obtain the desired slide image. Let's conclude. In this work, we introduced the LecSD, a comprehensive collection of lecture slide decks with 2 tasks of retrieval of lecture slide images based on brief descriptions that include logical regions and figure classes, and retrieval of lecture slide images using hand-drawn sketches of the figures as queries. We proposed an effective new retrieval model called Lecture Slide Deck Search Engine, which is semantic labels aware and includes sketch-based retrieval functionality. Lecture Slide Deck Search Engine does have a few drawbacks. First, it relies on an off-the-shelf layout segmentation module. Lastly, the model needs more success in searching slides from unseen subjects. We leave addressing these as the future scope of this paper. Thanks for your attention. If you have any question, please